Is my screen visible now?
Yes, it is visible. You can start.
Okay. Hello, everyone. My name is Oladotun, and I will be presenting this work titled Studying the Applicability of Proof of Reputation as an Alternative Consensus Mechanism for Distributed Ledger Systems. My co-author is Dr. Anton. So in this presentation, I will start with some introduction. I will go over some methods through which the research was carried out. Finally, I will close out with some experiments and some attack surface analysis. So to some introduction, a critical requirement for for blockchain-based systems is the ability to maintain a live decentralized transaction ledger while defending against attacks from Byzantine nodes or Byzantine actors. Consensus is central to distributed ledger systems, and it generally refers to how some shared state is agreed upon by a set of distributed nodes. And the applicability of any consensus mechanism is generally based on three properties. The first is safety, the second is liveness, and the final is the fault tolerance characteristics. And there are several crucial factors to consider in the design of a consensus mechanism. Some of them include node failure, network latency, network partition out of order inputs, and finally, node behavior. And specifically in this work, we focus on the node behavior as the basis for which the system is designed. So the most common approach to building consensus among participants is evidence or proof-based, and examples of other consensus mechanisms that use this approach is the proof of work, proof of stake, which I'll review later in the related work section. And as the nature of peer-to-peer networks is open and dynamic, the security risk within this kind of systems is greatly increased. And one way to minimize risks associated with this type of open communities is to use community-wide reputation as the basis for which interactions between nodes within the network will be judged. And historically, reputation systems have been employed to facilitate trust between entities when anonymity is key to the operation of the system. So the specific contributions of this work addresses the problem of designing an efficient and secure mechanism for distributed ledger systems or distributed multi-agent systems. And this kind of systems have been seen in applications like decentralized finance, swarm intelligence, or distributed artificial intelligence. So first of all, this consensus mechanism is based on the reputation of participants in the network, and it leverages the interaction between the nodes in the network over a particular period of time to determine the amount of reputation associated with each node in the network. Also, we in turn use this reputation to determine a set of consensus nodes that are then responsible for maintaining the shared states in the network, and also the calculation of new reputation values for other nodes within the network as the network progresses through time. Also, our novel approach to reputation consensus is based on social choice functions as a means to determine the integrity of data in the consensus group. Furthermore, the reputation system is based on the following principles. Number one, the liquid nature of the reputation values. That is, we use a recursive mechanism for calculating reputation values such that newly generated reputation values are based on initial or previous reputation values that were earlier calculated in the network. The second is the temporal scoping of reputation values such that the newly generated reputation values have more impact on the overall reputation than the earlier generated reputation values. And the last is the openness of all the reputation values so that all the nodes within the network are aware of the reputation values of all other nodes within the network. Finally, we develop an experimental model and we evaluate the performance of the system. So some related work to this are the proof of work or the proof of stake consensus algorithm, which are by far the two most popular consensus algorithms. And a more closely related work is an earlier consensus algorithm that was proposed by Yu et al., which is the RepuCoin. It's termed RepuCoin. It's also a reputation-based consensus mechanism that leverages the proof of work consensus algorithm as the basis for progressing the blockchain. So to some system overview and threat model, we make the assumption that the system is a strongly synchronized system. And what that means is that the nodes are connected by a network over which information is propagated through the exchange or the broadcast of messages. In our approach, we also consider that the network is untrustworthy and unreliable, which means that these messages that have been broadcasted to the nodes within the network can be delayed, they can be duplicated, or they can be lost. And we also assume that there is a social community upon which the system is based, and this social community is what facilitates the interaction between the nodes in the network. And then we say that each node within the network is identified by a public key and the corresponding secret key, which it can use to append its signature to transactions that happen within the network. So within our system, each transaction group is made up of two nodes. There is the first node, which we can term the rater node, which is the node that is giving a rating value to another node. And the other node within the transaction group is called the receiver node, which is the node that is receiving a rating, always in respect to some service that is rendered. So an example would be a node is performing a service within the network. So whenever the service is performed, the receiver of the service is going to give a rating to the provider of the service. And during the consensus phase, a node can either be a leader of the consensus group or simply be a member within the consensus group. And so we denote the total number of nodes in the network as N. We denotes the total number of faulty nodes as F, and these faulty nodes are made up of two types of nodes. The first is the Byzantine node, which is a node that is acting in a way that is counterintuitive to the entire goal of the system. And the second type of a faulty node is a sleepy node, which is any type of node that is experiencing some difficulty, maybe some network difficulty in participating in the entire network. So we restrict the adversary control to at most F nodes, where we follow the standard formula where we say 3F plus 1 is less than N, where we're saying that the total number of faulty nodes is at most this particular number. And we also assume the presence of this adversary, and we say that the adversary can control all the faulty nodes and can coordinate their behavior in some way. So more specifically, the consensus operates as follows. We assume N nodes within the network, and an individual node is represented as Pi, where I is an element of N. The interactions between the nodes are described as transactions, and we denote that as a tuple containing 3 elements, E to the subscript SKI, which is the encryption of the data that is signed by the secret key of the provider, the public key of the receiver, and finally R, which is the rating, which is a value between 0 and 1. We select the consensus group members from the nodes with the highest reputation values for which their collective reputation scores are over 50% of the total reputation values of the entire network. And then we denote a consensus node as PK to the subscript I, which is a subset of GK. GK here is the consensus group for a particular round K. So each leader, for each round, we select a leader at random from the consensus group. And for every selected leader for each round, it can serve three purposes. The first is to package all transactions from the list of pending transactions to a particular block. This block is going to serve as the proposed block, which has not been appended to the chain yet. And then the second function of the leader is to calculate the new reputation values for all network nodes for reputation K for the round, for the current round, using the data in the transactions, using the data from transactions in the transaction list. And then finally, it's going to broadcast the commit message to the consensus group. Then the leader, after packaging all the transactions from the recent time window in order, and it adds it to the proposed block, the leader is going to send this commit message to the consensus group, and then we denote this commit message as a tuple containing 4 elements, the proposed block, the public key of the leader, the hash of the block, and then the newly generated reputation list, which is going to be generated from all the transactions that have been added to this proposed block. And then each node within the consensus group is going to check the commit message sent by the leader, which contains the block and then the hash, and the tuple from equation 3. And then it's going to check for the integrity of the hash using the public key of the leader. And it's also going to check for the validity of all the transactions within the block. So each node that successfully verifies the block and the reputation list is going to send a verification commit back to the consensus group, which we also denote as a tuple, almost similar to the one in equation 4. So each node in the consensus group has an associated weight, W, that is assigned to it, which is equivalent to its reputation value from the previous round. And during the consensus process, there is a minimum quota, Q, which has to be reached for decisions to be made. So from the previous equation 4, the verification commit that is sent by each node in the consensus group constitutes a consensus vote. And then this vote is summed up in the process of arriving at the consensus. And then we set the quota as 2/3 of the total weight in the consensus group. And the consensus is only reached by a social choice function through the satisfaction of this necessary condition, DG, which is either going to be 0 or 1, depending on if the sum of the votes in favor of a decision is greater than the quota, which is 2/3. For cases where the decision is 0, that is the sum of votes is less than 2/3, we loop over this process and then we continue until we are able to arrive at a decision. So to the reputation system, each node, the node ratings are generated from node interactions on the basis of the liquid rank algorithm. And a node can receive multiple ratings for each time window or for each period. And then we denote the rankings as a list of rankings that are generated towards I from other nodes within the network. After we receive a list of all the rankings that are generated for a particular time period, we take the rankings and then normalize that set of rankings using the formula in equation 6. And afterwards, we then calculate a general ranking, which we denote as P, which is then calculated as S multiplied by R. S here is a column vector that consists of the normalized reputation values, and then R is a row, S is a row vector, sorry, which consists of the normalized reputation values, and R is a colon vector, which consists of the corresponding reputation values of the nodes that are providing the rankings in S. So the final reputation value is calculated for a particular round K using the formula on line 8. We blend the general ranking P with the previous reputation value for the particular node we are trying to calculate the value. Alpha here is referred to as a forgetting constant, and depending on how the value is set between 0 and 1, we give preference to either the general rating P or the previously generated reputation value R to the subscript K minus 1. So to prevent reputation values from upping, we clamp the values using a sigmoid function. So we take the values generated with the equation on line 8, and then we use a sigmoid function, and we define that sigmoid function on line 9. So for experiments, we built an experimental network. We implemented the mechanism and deployed the nodes on AWS EC2 clusters that are running 16 gig of RAM. We imposed a round trip latency of 200 milliseconds to try to simulate the effects of a wide area network. And then we varied the node setup between 500 and 1,000 nodes. We also added rate limiting to curtail the excess bandwidth usage. And finally, we benchmarked the system with Apache Bench. In the first experiment, we measured the throughput against the number of nodes in the network. And from our experiments, the results show that as the number of nodes within the network increases, so does the throughput of the system increase. In the second experiment, we measured the average block time. So by varying the block size between 100 and 500, we measured the time it takes for a new block to be appended to the already existing chain. And the results show a linear correlation. In the third experiment, we measured the consensus time. So by varying the block size again from 100 to 500, we measure the time it takes for the consensus group to arrive at a new consensus, to arrive at a consensus concerning the shared state of the system. And in this table, we compare our solution with some of the existing consensus mechanisms, and the results show that our system is only outperformed by the delegated proof of stake on the last line, although we can argue that through some code optimizations and some better development environments, we could easily outperform the delegated proof of stake. And so in this figure, this is some results of some attack resilience analysis of the system. With the graph on the left shows the probability of a malicious leader selection as a consensus group leader as the consensus group size increases. So we see the probability drops as we are increasing the consensus group size, and the interpretation of that is that as this probability drops, the system is significantly more secure. So even as we increase this consensus group size the more, we're going to see a significant drop in that probability value, which translates to a better secure system. And the graph on the right shows the number of nodes that need to be controlled by a malicious node for the security of our system to be hampered. So we show, we vary the consensus group size between 100 and 600, and then the results show that there is a linear correlation between the consensus group size and the number of nodes that need to be controlled. So as this consensus group size increases, a malicious node will need to control even more nodes to effectively hamper the security of the system. And so in this table, we show our system, as it's secure against some of the popular attacks like the flash attack, the selfish mining attack, and the eclipse attack. So this concludes my